As we look at the second part of our Lineocentrism notes, I just want to highlight that, again, I've got some written notes here in terms of a scammed file, but most of the stuff we're going to go through here comes straight from our the printed skeleton notes, getting you to think about things, fill them in on your own. So I would first like you to read through these two bullet-pointed quotes up here, and after you have, look at A and B and see if you can come up with responses to A and B. So go ahead and pause the video. I know you just started, but pause the video and come back once you've looked at A and B and tried to get some response to them. Alright, so welcome back. As we look at these quotes, all right, what's happening anytime these sort of editorialists or whatever produce these figures, what they're doing typically is they're using proportions. Even the word proportionally is involved in one of the quotes. And so what that's doing, for those who are unfamiliar, is they are setting rates equal to each other. So 1,074 Israeli citizens, for example, who perished, compared to Israel's population, would be equivalent to how many Americans related to the U.S. population. Right? In other words, proportions are setting these rates equal, right? And oftentimes people think these rates should be equal. So the question is this good reasoning? All right? And this comes from Jordan Ellenberg's book, How Not to Be Wrong. And so what we're doing here, what we have to be careful here is as you scale up and down a population, that changes the number of deaths by tragedy that is apparently equivalent, right, in different settings, different contexts. And there are several reasons I might argue that it wouldn't be good reasoning. One is you are sort of removing the humanity of the issue. But the attempt is to contextualize things for a certain community that might be apart or not understand how big or small an event is in affecting the local culture, or the local community that it is actually affected by. So there's pushback there. But another example, mathematically speaking, why this isn't a great tactic is that, say there's a bar fight. There are two people in a bar. Two people. There's a bar fight. One punches another. So 50% of the population got hit. So is that equivalent to 160 million U.S. citizens getting hit in the face with a punch? Well, no. But the problem is that when we apply these mathematical methods, all right, we feel like they should be able to work regardless of how we're trying to compute things, if we're trying to compute the same different thing. And that's an important mathematical rule for mathematical modeling here. When you're field testing a method, all right, try computing the same thing several different ways. If you get different answers, that means there should be a problem. So my example here, what I mean here is, let's take the 2004 bombings in the Madrid train station. 200 people were tragically killed. Right, which is a very low, small percentage of the Spanish population. All right, so if we compare that, all right, in fact, I'll come over here in the Madrid example. 200 compared to Spain's population is approximately how many compared to the U.S. 2004 population? Well, that's 1,300. All right, in other words, that would be equivalent to 1,300. All right, U.S. citizens. Okay. Well, the problem is if we try computing the same thing to give us give us perspective relative to, instead of U.S., Madrid happens to be a city in Spain. I believe it's the biggest city still. And so 200 people relative to the Madrid population, it's a larger percent of the Madrid population, but would be how much compared to, for example, the New York City population? Well, if we computed it this way, it would be 463. All right, New York City, all right, citizens would be the proportionally equivalent number. Well, what if we compared it instead, Madrid, the province of Spain, compared it to the New York State population? Well, then we're at 600, all right? So that would be 600 New York State, all right, citizens. Well, so these are all three different numbers, and one of them is quite a bit different than the others, right? And so we're trying to compute the same thing in some different ways, and we're getting very different answers. That's an issue, right? So it's a red flag, all that sort of stuff. But so although proportions can be fishy, in this scenario, for example, they do matter, right? They really do matter. And so let's look at this example. I'd like you to take a minute, read through this example, all right, and answer the following question in terms of if we're looking at trying to figure out which parts of America have the biggest brain problem. Does it make sense to look at states with the most deaths, all right, from brain cancer? So take a second, pause it, and tell me why it does not make sense to do that. If you're coming back to me, if you've paused, take a second, come back. One of the reasons it's not going to make sense to do that is, for example, in California, we'll expect to have more instances than in, let's say, Maine, right, or Montana. Why is that? Well, the population of California is much greater, right? So even if we've got a certain occurrence of brain cancer issues, right, the mere fact that more people live in California, we should expect more occurrences just as raw numbers or absolute numbers. Okay, so that's why we say here it may be better to study rates. Okay, so in this case, the top 5, all right, states, the highest rates in terms of brain cancer, I'll say occurrences, are South Dakota. It appears I've abbreviated all of these in a weirdly different way, but South Dakota, Nebraska, Alaska, and Delaware, and Maine. The bottom 5 are Wyoming, Vermont, North Dakota, Hawaii, and DC. So now that begs a question. South Dakota is in the top 5, and North Dakota is in the bottom 5. All right. So let's say most occurrences and fewest occurrences. So here's my question. Why should South Dakota have a problem and North Dakota be nearly tumor-free? What's at play here? Right? So take a second and try to figure out what's really at play here. What's going on? So if you pause the video, you could unpause it now. And what's happening here is, well, we're looking at rates. So in other words, we're comparing, make sure we're all clear on what we're doing, is we're comparing, number of occurrences. Let's say number of occurrences. Let's see if we can still spell occurrences, barely. All right, and we're comparing in a certain state, okay? And we're comparing that to, don't want that. It's going to make some big mess. Right? The actual population of that state. Right? That's what we mean when we say rate. Same way as we were doing here when we were comparing proportions, we were setting rates equal to each other. So we're looking at the number of occurrences in the state versus the population of that state. And that's giving us our rate of brain cancer occurrences. Well, what's happening is that these states are all in the bottom, I believe, 13. So in other words, the most populous state of all of these right here, I believe, is Nebraska. All right. And it's the 37th largest state or district. Okay. So they're all smaller. Okay. So when we have smaller sample sizes, all right, one occurrence in terms of one brain cancer occurrence is more of the population as a percentage than it would be in, for example, California, right? The same way 1 out of 10 is a greater percentage than 1 out of 100. So when we've got smaller states or smaller data sets or population sizes, sample sizes, we'll say population sizes, all right, there's more variance because each occurrence, all right, is more of the overall population. So for example, we're going to illustrate what's going on by flipping coins. Let's say we flip a bunch of coins. All right, so I'm right here now. Let's say we flip a bunch of coins, and whoever gets the most heads wins. But not everyone has the same number of coins. Let's say we've got a big stack versus a little stack. So Cassie's got 100, and I've got 10. Okay, who do we expect to get raw numbers, absolute numbers? Who do we expect to have more heads? Cassie. She had 100, right? So she should definitely, almost certainly, get more heads than I will, right? But now if instead we look at proportion, if we score by proportion or rate, all right, we'll say rate, if we go to how many times heads showed up, so the rate of heads, we'll say the number of occurrence of heads versus the total throws, all right, Now we're getting closer to something that's meaningful, all right? Because it's taking away the advantage Cassie had from having more coins, okay? So we now are looking at rate of heads versus total throws. Well, the more coins we throw, the closer our ratio is going to be to 50-50, assuming the coins aren't weighted, oddly, right? Hopefully we'll get closer to 50-50, right? And we'll revisit this idea later, this idea of what we're going to call the law of large numbers, right? But the more we throw, the more we expect, all right, reality to get closer to 50-50. So my question is now, all right, if we've got 100 coins, all right, so Cassie's got 100 and I've got 10, all right, I get 7 heads versus Cassie getting 70 heads. Which one of those is more likely? In other words, here I got 7 out of 10 to be heads, so I was off of 50-50 by 2 occurrences, right? 2 small occurrences of heads, or 2 more occurrences of, for example, brain cancer, made up 20% of my total. Right? Whereas over here, we needed 20 more heads or 20 more occurrences in order to make up that same percentage. Okay, so when we've got a smaller population, right, there's more variance. Okay, the more data we collect, in other words, the greater we let our population become, right, in terms of flipping coins, the closer we expect it to get to be 50-50. One of these, this one is very unlikely to occur right here. I'm going to circle it with some other color. Purple's a good color. All right, this instance over here, that's a good looking circle lean, is very unlikely to occur. Okay. As coming back to our examples of both brain cancer and flipping coins, the whole idea here that I'm trying to highlight is that absolute numbers make larger states or events win in the sense, or lose in the sense of cancer. In other words, California is expected to have more occurrences than Vermont. However, rates put the smallest states in the lead. Mainly, I mean, there's more variance. All right, smaller populations have more variance, which allows the rates to fluctuate more, both up and down. Right, because one more or fewer occurrences of something will be more of an influence over towards the total rate, the total percentage, just like with our flipping coin example. So a third discussion question might be, find an example where either absolute numbers or rates are causing an unfair advantage or disadvantage in the data being presented. So for example, have you seen any places, or could you find a place where someone's talking about comparing states and maybe what we're comparing depends on population and they're going by strictly absolute numbers? Well, maybe it's not fair. All right, this often happens when we talk about budgeting, all right, that sort of thing. So this ends our Lineocentrism sort of notes, our section. Look for more information about discussion questions, submitting them, as well as based on content, as well as an article and brief assignment for week 1.